Suppose you are given 192.168.100.0/24 and need 4 equal subnets. To create 4 subnets, you borrow 2 additional bits from the host portion, which changes the prefix from /24 to /26. That produces 4 subnets: 192.168.100.0/26, 192.168.100.64/26, 192.168.100.128/26, and 192.168.100.192/26. Each /26 subnet contains 64 total addresses. In traditional IPv4 subnetting, one address represents the network and one represents the broadcast, leaving 62 usable host addresses. This is a realistic example for small branch segments, departmental LANs, or service partitions. The exact arithmetic matters, but the operational point matters more. Subnetting creates boundaries that routers understand and enforce. Those boundaries are what make routed communication scalable. Now that we understand addressing and subnets, let us look at how routers actually choose where to send packets. Routers forward IP packets using a process called longest prefix match. When multiple routes could match a destination address, the router chooses the most specific route, that is, the one with the longest prefix length. For example, imagine a routing table containing both 10.0.0.0/8 and 10.1.2.0/24. If a packet is destined for 10.1.2.50, both routes technically match, but the /24 route is more specific and therefore wins. This behavior is essential because it allows networks to summarize broadly while still directing traffic precisely where needed. Longest prefix match is one of the most important ideas in routing and forwarding. It explains why detailed routes can override broader summaries and why route design must be deliberate. Before a router can send a packet to the next hop on an Ethernet segment, however, it often needs one more piece of information: a MAC address. Address Resolution Protocol, or ARP, is used in IPv4 networks to map a known IP address to a corresponding MAC address on the local link. If a host or router knows the next hop IP but not the next hop MAC address, it sends an ARP request asking, in effect, who has this IP address? The device that owns that IP address responds with its MAC address, allowing the sender to build the Ethernet frame correctly. This information is typically stored temporarily in an ARP table or neighbor table, so it does not need to be rediscovered for every packet. ARP is local in scope. It does not resolve remote destinations across the Internet. A host does not ARP for a server in another subnet. It ARPs for the local default gateway. That distinction is central to understanding packet delivery. Next, we will connect ARP directly to forwarding behavior on a routed path. When a host sends traffic to a destination in the same subnet, it uses ARP to learn the destination host's MAC address. When the destination is in another subnet, the host instead uses ARP to learn the MAC address of its default gateway. In both cases, ARP supports the immediate Layer 2 delivery decision. Routers use the same logic on outgoing Ethernet interfaces. If a router needs to forward a packet to a next hop on a directly connected Ethernet network, it must know that next hop's MAC address. Without successful ARP resolution, the IP route may exist in the routing table, but actual frame transmission cannot occur correctly on that segment. This is why troubleshooting often requires looking beyond the route itself. A route can be present, yet forwarding still fail because adjacency or neighbor resolution is incomplete. To round out the IP fundamentals, we now turn to ICMP, a protocol many engineers first encounter through tools like ping and traceroute. Internet Control Message Protocol, or ICMP, is used for control, error, and diagnostic messaging in IP networks. One common use is the echo request and echo reply pair used by the ping tool. When you ping a device, you are testing whether it can receive and respond to ICMP echo messages. ICMP is also used to report conditions such as destination unreachable or time exceeded. Traceroute relies on this behavior to reveal the path traffic takes through the network by triggering replies from intermediate devices along the route. It is important to remember that a successful ping does not prove that every application will work, but it is often an excellent first test of basic reachability. Likewise, a failed ping does not always mean the device is down, because policies or security controls may filter ICMP. The real value of ICMP is that it gives operators a simple way to test path behavior and error conditions. We will close this section by tying the IP pieces together. We now have a practical foundation in IPv4 behavior. IP addresses identify interfaces logically. Prefix lengths define subnet boundaries. Routers forward using longest prefix match. ARP resolves local next-hop MAC addresses so Ethernet delivery can occur. And ICMP provides control and diagnostic messaging that helps operators verify reachability. These are not isolated topics. They interact continuously. A host determines whether a destination is local based on the subnet. If remote, it uses the default gateway. The router performs a route lookup, resolves the next hop, and forwards the packet. If something fails, ICMP may help reveal where the path breaks. With IP fundamentals in place, we are ready to study how routers learn routes in the first place. That brings us to static routing, dynamic routing, and the major routing protocol families.